Welcome and thank you for joining us for today's webcast, the ANCER for Corrosion and Erosion Protection on Copper Microchannel Coolers, sponsored by Advanced Cooling Technologies and TechBriefs Media Group. I'm Billy Hurley, Associate Editor with TechBriefs Media Group, and I'll be your moderator today. Our webcast will last approximately 30 minutes, and there will be a question and answer period at the end of the presentation. If you have a question, you may submit it at any time during the presentation by entering it in the box at the bottom of your screen. Our presenters will answer as many questions as possible at the conclusion of the presentation, and those questions not addressed during the live event will be answered after the webcast. Also, twice during the presentation today, we will present you with a poll question, which we invite you to answer at the appropriate time. In order to view the presentation properly, please disable any pop-up blockers you may have on your browser. At this time, I'd like to introduce our speakers. Pete Ritt is Vice President of Technical Services for Advanced Cooling Technologies. Mr. Ritt joined ACT in 2010 to head ACT's technical services business. During this time, the group has successfully provided thermal consulting, design, and prototyping solutions to commercial customers in the lighting, renewable energy, industrial equipment, and medical industries. Also on the line for our Q&A today is Matt Flannery, R&D Engineer in the Defense Aerospace Group at Advanced Cooling Technologies. Flannery joined ACT's Research and Development Group in 2011. During this time, he has led the technical efforts in multiple DARPA, DOE, and Air Force-funded research programs in nanoscale coatings for erosion and corrosion protection, hybrid solar and coal gasification, and the combustion of aviation fuels by utilizing nanoparticle technology. So now I'd like to hand the webcast over to our first speaker, Pete Ritt. Pete?
Thanks, Billy. About a year ago, we held a webinar on a new coating we call an ANCER that showed excellent results in minimizing corrosion and erosion issues in copper microchannel coolers, MCCs, used in laser diode thermal management. The response from that webinar was unbelievable, and with encouragement from many parties, we'd like to give you an update on the progress of the product and the technology over the last several months. We'll start by providing some background on ANCER, the problem being solved by it, and some baseline measurements. Then we will show updated lifetime trends as well as initial results on aluminum, which, while preliminary, are showing the same positive trends we saw on the early work on copper microchannel coolers. By way of introduction, ANCER is a thin, conformal coating that our testing has shown to provide superior resistance to corrosion and erosion on copper microchannel coolers. These corrosion and erosion problems have plagued the laser cooling diode industry for some time. The most effective solutions usually have significant cost and complexity associated with them. Many people experienced in the microchannel cooler world told us that they have heard these types of claims before. So today, we'd like to review the ANCER coating, discuss some of the benefits, and summarizing our testing that has led us, and more people every day, to conclude that a solution for corrosion erosion effects on copper microchannel coolers is now available. After reviewing these most recent results, we'll conclude by answering some questions. Laser diodes are used in many different industries, including defense, medical devices, and analytical instruments. They are generally grouped together or stacked to increase overall optical output. The laser stacks require a uniform temperature to operate, but generate significant amounts of waste heat. If left unchecked, the higher temperatures can result in unwanted increased wavelength shift and overall deteriorated optical performance of the laser diode. A common cooling solution for these laser stacks is to use a pumped liquid system, where the working fluid removes the waste heat and dissipates it through a chiller or other heat exchanger. Deionized water is frequently selected as the working fluid. To ensure long-term reliability of the cooling channels, the water quality needs to be closely maintained for several parameters, including temperature, flow rate, dissolved oxygen, pH, and resistivity. Water that has dissolved oxygen and pH values that are too high or too low can enable the formation of particulates that block MCC passages, thereby reducing the thermal performance of the cooler. The cooling element that is in contact with the laser diode is a complex, multi-level copper microchannel cooler. A sample copper microchannel cooler can be seen on the lower right. High flow rates of DI water, which are necessary to provide the temperature stability for reliable laser performance, can also induce corrosion and erosion defects, causing unpredictable and catastrophic failure. Until now, there has been no accepted solution for these corrosion erosion defects, but we believe that is changing with ANCER. Let's examine the problem a little closer. As we just mentioned, the laser diodes are cooled by a single-phase coolant, typically DI water. The laser diodes are usually stacked, as can be seen in the figure on the left, with the diodes mounted on the microchannel cooler. The high velocity flow rate of the DI water is erosive and corrosive to the base copper material. Small defects, imperfections in the copper layer can become dislodged as a result of the fast flow rate. The particulates can build up over time, causing flow restrictions or clogging along some of the microchannel cooler's flow lines. Simultaneously, flow rates with linear velocities of greater than 2 meters per second can strip the native oxide off the copper surface. Seen in the schematic on the right is the corrosion equation. The presence of bare native copper with water and oxygen causes electrons to separate from the copper. The free electrons combine with the water and oxygen to form a hydroxyl group, which then combines with Cu+2 to form copper hydroxide, which is subsequently converted to the native copper oxide. Let's take a look at how devastating these erosive corrosive effects can be. The pictures are from a paper given by Ceramic at Photonics West a few years back. The paper is referenced at the bottom of the slide. As we have mentioned, high-velocity DI water degrades the heat transfer surfaces by either making them thicker or thinner than the intended design. Today's copper microchannel coolers are highly engineered devices having 5 and 6 layers, each with unique features. These smaller features are more susceptible to degradation. The picture on the left is a cross-section of a virgin copper microchannel cooler. The picture on the right is that same cross-section after being exposed to 15,000 hours of a 0.5 megaohm cm DI water system at a flow rate of 0.5 liters per minute. The degradation can be seen on the right is quite obvious. Currently, the solutions for minimizing corrosion erosion defects in copper microchannel coolers are to 1. Have a tightly controlled DI water control system, 2. Deposit a gold plating on the MCCs, and or 3. Execute a rigorous maintenance plan and replace the coolers before they are likely to cause problems. All of these solutions have drawbacks. The tightly controlled water systems are costly to implement and maintain, and, as we have seen, can actually contribute to corrosion erosion effects. Gold plating can provide good protection, but the liquid coating process is incapable of providing a pinhole-free, truly conformal coating for the complex, high aspect ratio internal features of these microchannel coolers. The presence of pinholes can result in some of the erosion-corrosion effects that we are trying to eliminate. Routine maintenance replacement of the microchannel coolers is expensive, not only in terms of cost, but also in loss of productivity from extra downtime. So it is a problem currently without a good solution. ANCER stands for Applied Nanoscale Corrosion Erosion Resistant Coating. It is a new coating solution that is entering the commercial sector after multi-year development by Advanced Cooling Technologies. The project is being funded by DARPA, the well-respected Defense Advanced Research Projects Agency, which has been responsible for many new technology innovations. Science Research Labs, SRL, was a key contributor. ANCER uses a chemical vapor deposition process to apply a thin, nanoscale conformal coating across the surface substrate. The readily controlled vapor deposition enables the ANCER coating to be uniformly applied on difficult-to-reach, high aspect ratio internal features of microchannel coolers. Further, the deposition process is readily scalable to handle more or larger parts. Our testing of the ANCER coating has shown it to be very effective in preventing corrosion and erosion effects. We'll share our results with you today. And testing has commenced on aluminum to determine if the same benefits can be realized there as well. The previous slide introduced the ANCER coating. Here is a summary of its benefits. The chemically inert coating has shown to exhibit a significant reduction in corrosion rate compared to gold plating. We've seen how high velocity coolant flow can produce negative erosive effects. ANCER is a barrier coating that prevents that. The self-limiting deposition process can cover small defects on the surface substrate, producing a pinhole-free coating. The vapor deposition process ensures uniform coating even on complex geometries, which are inaccessible to other liquid coating and plating techniques. The coating is durable. Repeated thermal cycling tests have demonstrated superior bonding between the ANCER coating and the underlying copper substrate without impact on corrosion resistance. The superior coating strength and durability allows a wider range of coolant specifications of flow velocity, dissolved oxygen, and pH, allowing more relaxed operational requirements without affecting MCC performance. So there's the major advantages of ANCER. Let's now look at some testing results to explain why we are so excited about this new solution. But first, we'll turn it back to Billy for a polling question.
All right, Pete, now it's time for our first poll question today. It will appear on your screen now. The question is, who does your company use to resolve critical thermal management issues? Your choices are A, in-house resources, B, external experts, C, a combination of both in-house and external resources, or D, not sure. So you can make your choice by selecting the appropriate button on your screen. Again, who does your company use to resolve critical thermal management issues? And as you make your selection, I will hand the presentation back over to Pete Ritt. Pete?
Thanks, Billy. Here is a contour plot that demonstrates that the ANCER coating offers the opportunity to relax the requirements of the cooling water. In this test, bare copper samples and ANCER-coated samples were measured for corrosion rate under a variety of pH and dissolved oxygen settings. Resistivity was held constant at 0.3 megaohm centimeter throughout. The many colors on the bare copper plot on the left indicate an order of magnitude variation in corrosion rate from approximately 0.0083 to 0.33 millimeters per year. Recommended water control regions have a dissolved oxygen of approximately 1 to 3 parts per million and a pH of approximately 7 to 7.5. which occupies only a small portion of the plot. The ANCER-coated samples on the right showed essentially no variation across both test parameters, indicating that with ANCER-coated microchannel coolers, both dissolved oxygen and pH requirements can be relaxed without any negative consequences in erosion-corrosion protection. This offers the potential to save money in both equipment and operational costs. Another good question that has been asked is how can you confirm that the coating is present and its thickness adequate over the MCC internal structure? The measurement is not trivial because the coating is very thin, around 100 nanometers or so, and somewhat transparent. To provide a discrete spot measurement, ACT, with its partners at Penn State, has developed a focused ion beam scanning electron microscopy technique, FIB-SEM for short. In this technique, as can be seen on the left, a sacrificial layer is deposited on top of the ANCER-coated sample. A focused gallium ion beam is then used to make a cross-section of the copper plus ANCER plus sacrificial layer piece. That cross-section area is then viewed with a scanning electron microscope. A sample SEM is seen on the right. The top diagram shows the location in the microchannel cooler where the samples were taken. The actual SEM images are seen below that. The darker gray on top, number 1, is the sacrificial layer. The lighter area in the middle, where the ANCER coating is number 2, and the copper base is below that, number 3. As can be seen here, both locations have thicknesses of approximately 100 nanometers. Of course, the entire coating is not at precisely 100 nanometers, but good uniformity, plus minus 25 nanometers, has been achieved. Here we test if the ANCER coating affects the heat transfer performance of the MCCs. To do so, we utilize head-to-head H2H copper microchannel coolers from SRL. H2H is a single cooler with two coolers integrated head-to-head. One head is connected to a high-temperature coolant flow, which serves as a heat source, and the other head to a low-temperature coolant flow, which serves as a heat removal mechanism. Measurement of the delta T across the coolers enables the thermal resistance to be determined. The overall thermal resistance network is seen next to the experimental setup. The samples were tested before and after the ANCER coating was applied. As you see on the plot on the right, the lines before and after coating are on top of each other. From this we conclude that the ANCER coating does not impede or degrade the thermal performance of the microchannel cooler. So we have shown that the ANCER coating provides significantly lower corrosion rate, but does not affect the thermal performance of the copper microchannel cooler. Let's next look at whether the coating affects flow performance. Again, we showed results for an uncoated and then ANCER-coated sample at 0 hours of life. Here we are measuring hydraulic performance, the pressure loss across the microchannel coolers as a function of flow rate. This is a test to determine if the ANCER coating affects the flow of the highly engineered microchannel cooler internal features. Hydraulic performance can change by either restricting or expanding flow channel dimensions. Again, we see that before and after coating results are identical, and we conclude that the copper has not affected the design flow path of the MCC. We'll next look at some accelerated life tests, but before that, we'll turn it back to Billy for the final polling question.
All right, it's time for our second and final poll question. It will appear on your screen now. And the question is, are you facing any thermal management issues in the next A, 0 to 6 months, B, 6 to 24 months, or C, you're having no immediate issues? And you can make your choice by selecting the appropriate button on your screen. Again, when are you facing thermal management issues? 0 to 6 months, 6 to 24 months, or C, no immediate issues. And as you make your selection, I will hand the presentation back over to Pete Ritt. Pete?
Thanks, Billy. Next, we test whether ANCER coating can provide stability in hydraulic performance over a 200-hour test. Again, test conditions are listed on the left. Note that the pH of 6 was selected, but the corrosion rate of copper is 10 times greater at pH of 6 than at pH of 8 for DI water systems. Results for both the coated and uncoated samples are plotted on the right. ANCER are the solid lines and bare copper are the dotted ones. Both ANCER samples again are on top of each other. However, 5% deviation from the starting point can be seen in both uncoated samples. The deviation above the solid ANCER-coated samples suggests a flow restriction caused by a blockage. The dotted line below it suggests expansion of the flow channel due to some erosion and corrosion effects. The two ANCER-coated samples are virtually identical, indicating stable performance. Next, we'll reevaluate the thermal performance of the coated and uncoated coolers after the 200-hour test we described in the previous slide. Again, the ANCER-coated sample showed a less than 1% change in thermal resistance after 200 hours. The uncoated sample showed a 5% increase in thermal resistance, a measurable change, particularly when MCC failure is typically determined when the microchannel cooler shows a 20% increase in thermal resistance. Before we look at more extended life test results, let's take a quick look at the test setup. Remember, as the results from the previous slides indicated, we are starting the testing knowing the ANCER coating deposition has not affected the initial thermal performance of the MCC. For these tests, we use commercially available microchannel coolers from a well-known supplier. In both the uncoated and ANCER-coated stacks, chip heaters were first soldered to the diode bond region prior to assembly. In the pictures on the lower right, you can see where the MCC stack is located within the test setup. The picture on the right shows the location of both the baseline copper MCC stack and the ANCER-coated stack. Test setup parameters and values, including coolant pH, and heater power, are listed on the top right. The key metrics that are monitored include pressure drop, deionized water temperature rise, and chip heater power and temperature. Now that you have an idea of the test setup, let's look at some more recent, longer-term results. Industry standard for meaningful life test results is 10,000 hours. Unfortunately, there is only one reliable way to do that, and it does take time. But here we show results for testing the stack configuration detailed in the previous slide after 5,000 hours. Operating conditions are the same as the previous slide. On the graph, in the y-axis, we plot the normalized thermal resistance against time. ANCER-coated samples are the blue circles, baseline copper are the green ones. We see for the first 3,000 hours or so, there is no meaningful change in normalized thermal resistance for either of the samples. However, at this 3,000 hour point, the thermal resistance of the baseline sample is starting to increase, while the ANCER-coated sample remains stable. The trend of increasing thermal resistance has continued in the baseline sample and suggests some degradation in the bare copper, likely caused by erosion-corrosion effects. During this time, the ANCER sample remains unchanged. We'll just have to wait and see if the trend continues, but at this point, ANCER is providing long-term corrosion-erosion protection. We have been asked many times if the benefits we have shown in ANCER coating to provide on copper can be realized on other materials, especially aluminum, which is lighter and cheaper than copper, but still suffers from the same corrosion-erosion issues. For military applications, this would be particularly beneficial for high-energy laser devices, which are striving to become more transportable and are subject to weight limitations. Testing has been initiated to see if ANCER can become a reliable passivation coating for aluminum, and here we show initial results under the test conditions detailed on the right. We have only 150 hours of life data, but these early results are encouraging. Like we saw in the initial copper testing, ANCER-coated samples, seen as the green circle, have approximately 2 orders of magnitude lower corrosion rate than the bare 6061 aluminum sample. Again, we'll just have to wait and see, but these preliminary results are promising. In a minute, we'll show a quick 15-second video of the ANCER coating in action. The video shows a copper coupon that has ANCER coated all over the plate except where the ACT logo is, which was masked off prior to the coating process. The coupon is placed on a heater and raised up from 25 to 400 degrees C. You can clearly see the bare copper changing color from thermal oxidation. The ANCER-coated portion of the coupon remains constant throughout the test, a clear indication the ANCER coating provides a tight bond to the copper, which prevents the thermal oxidation, even up to 400 degrees C. We'll replay it a few times so you can see the dramatic color changes on the bare copper between 150 to 250 degrees C, and again between 250 and Okay, we'll go back to the presentation package. Also, within the last few months, ACT has upgraded our testing capability. We now can test MCCs. as operating laser diodes. This now gives us the ability to evaluate MCC performance under more realistic conditions, and we can monitor laser diode performance more accurately. The test cart can be seen on the upper left. Here, the laser safety enclosure, MCC stacks, and other critical items are called out. The picture to the right of that depicts the water-cooled beam dumps and integrating sphere. An overall system layout is seen below that. The testing capabilities enables more realistic MCC testing and evaluation. So let's do a quick review of what we presented today. The Applied Nanoscale Corrosion Erosion Resistance Coating, ANCER, developed by Advanced Cooling Technologies, can provide superior corrosion erosion protection for copper microchannel coolers. Electrochemical impedance spectroscopy, EIS, showed the ANCER coating reduces the corrosion rate of copper to values of less than both copper and gold-plated copper, and can maintain that corrosion rate over a wide range of dissolved oxygen and pH values. Thermal performance testing demonstrated that the ANCER coating does not impede the MCC operation. Ongoing 5,000-hour testing demonstrated that the ANCER-coated MCCs maintain consistent thermal resistance, while bare copper MCCs are showing some degradation under identical conditions. Preliminary results on aluminum have demonstrated 2 orders of magnitude improvement in corrosion rate in initial testing. Based on these results, we are confident in saying that the ANCER coating offers improved corrosion resistance with a chemically inert layer, improved erosion resistance with a hard coating that protects the copper from negative effects of high-velocity DI water systems, a complete conformal pinhole-free coating that can be uniformly applied even on difficult-to-reach internal features, a good, strong bond to the copper and now aluminum surface, a superior coating that can provide this high-level performance, enable relaxed DI water system requirements. It truly is the answer for corrosion, erosion resistance, for copper microchannel coolers, and perhaps many other things as well. We thank you for your attention, and we'll try to answer any questions that you might have.
Thanks, Pete. At this time, we'd like to begin our Q&A. So if you have a question, you can submit it by entering it in the box at the bottom of your screen. And now I'd like to welcome to the line Matt Flannery. Matt is the R&D engineer in the Defense Aerospace Group at Advanced Cooling Technologies. Matt, we already have some questions here in the queue. The first one we have, how do you confirm the presence of the coating analytically?
That's a great question. What we do is take the copper microchannel cooler and we will cross-section it and then use a FIB-SEM, FIB standing for focused ion beam, SEM scanning electron microscopy, as we showed previously, to cut a cross-section into the coating layer and observe it under SEM. Through that, we can determine the coating thickness visually on that surface. And we do this throughout the flow channel, throughout the length of the flow channel of the microchannel cooler, to look at the uniformity of the coating or the thickness distribution throughout the length of the channel. And that's how we evaluate the presence of the coating analytically in high aspect ratio channels.
Is there a significant difference between the coating process on copper versus aluminum?
There is not. Essentially, our coating occurs in the vapor phase, and the material that we would like to deposit the coating onto is just placed within the chamber, and we evaluate the growth rate of the coating on these different materials through that same FIB-SEM process to evaluate how that coating grows on the different materials. But as we showed in the webinar, the copper and aluminum coatings are possible.
An attendee had this question. Can you explain again the role of sacrificial carbon?
That's another great question. The role of the sacrificial carbon is to protect the ANCER coating during the focused ion beam cut. So in order to make that cross-section, we use that focused ion beam to remove away material. And because the coating is on the nanometer scale, any mechanical methods of cross-sectioning the coating layer would cause damage to that surface. So this carbon coating allows for any initial damage to occur sacrificially on the carbon coating as opposed to the ANCER coating, so that we get a pristine view of that coating thickness when we view it under the SEM.
Matt, this will have to be our last question as we're running out of time. How do you determine the corrosion rate, such as short time testing? And it says here the corrosion layer will be very thin.
Right, so in order to get corrosion data in a very short period of time, we use a process called electrochemical impedance spectroscopy. And in some of the test apparatuses that Pete mentioned during the webinar, we've built our own electrochemical cells in order to enable the electrochemical impedance spectroscopy to be conducted throughout a simulated duration of testing in simulated laser diode operating conditions. And through this, we get instantaneous corrosion rates as a function of time, which show us the erosion or the corrosion rate, and the erosion can be kind of simulated by the change in corrosion rate as a function of that exposure time.
All right, we'll end it there. That concludes today's webcast. Again, if we did not get a chance to answer your questions today, our sponsors will do their best to address them after today's presentation. So our thanks to Pete Witt, Matt Flannery, and everyone out there for joining us. And just a reminder, this webcast will be available on demand at www.techbriefs.com for the next 12 months. Have a great day.